Today we're going to do section 5, which are Cauchy-Euler equations. So yesterday we handled it when your coefficients were all constants. What if they're not constants, right? What if the coefficients are functions? Cauchy-Euler, though, is a specific type of having your coefficients be constants. So it actually turns out to be pretty nice. All right, so a linear differential equation is called a Cauchy-Euler equation. If it's of the form where you've got b naught x to the power of n times d n plus b1 x to the n minus 1 d n minus 1 plus dot 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 plus b n minus 1 times x now to the power of 1 d to the power of 1 plus bn, all operating on y equals 0, where all of the b's are constants. So b naught, b1, all the way through bn are constants. So you've got constants, right? They're not, these guys aren't functions as the coefficients. But do you notice that now you don't just have a constant as your coefficient on this differential equation, right? You've got x to the n, x to the n minus 1, all the way down until x to the power of 1. But hopefully what you notice is that each of these exponents match. Yeah, that's what makes it Cauchy-Euler, that the power on x matches the order of the derivative for each of the terms. Now, you got n minus 1, n minus 1. This is like an invisible 1, and there's a 1 there. And there isn't an x. It's like x to the 0. It would be on y. Okay, so that's Cauchy-Euler. And what's nice about this is we know how to solve differential equations when it's just constant coefficients. That was yesterday's lesson. And so what we're going to do is we're going to just change the equation. We'll do a substitution that will make our new equation be one with constant coefficients, and just by changing the independent variable. All right, so in order to solve, what you're going to do is do a nice little substitution of your independent variable. So to solve, what you're going to do is you are going to let x equal e to the t. Yeah, which also means that if you end up with a t, if you were solving for t on this equation, t would be the natural log of x. Yeah. So that's what we're going to do. That's the substitution we're going to do. Yeah. Which means that when I say y of x, that would be like y of e to the t. I'm going to rewrite this as I'm going to use a capital Y now to represent that capital Y is just a function of t. So we'll substitute these variables, we'll solve it, and then we'll go back and we'll replace our variables back in with x's. So we're going to solve it by rewriting it as capital Y of t. We'll end up having constant coefficients. All right, so what are the substitutions you're going to make? You're going to replace any lowercase y in your problem. We're going to rewrite it with a capital Y. This is y. I'm changing it to be a lowercase y as a function of x to a capital Y being a function of t. And then your book shows a proof of all of these. I'm not going to include it in this video, but if you're interested, by all means, go look. There's a proof of y, x times y prime, we're going to end up writing that as just capital D on capital Y. And they use the substitution of the variable, they use chain rule to prove it, and then they also use mathematical induction to show that it's true for all of it as you go down the line. These are each of our substitutions. So I'm going to be substituting when I see x, y prime, I'm going to substitute it with a capital D, capital Y. I'm going to substitute x squared y double prime as d times d minus 1 operating on capital Y, and I'm going to replace x cubed y triple prime, or the third derivative on little y, as d times d minus 1 times d minus 2 operating on capital Y. Again, the proof of why these happen are in your book. Chain rule, the substitution, chain rule, doing substitution again, and then mathematical induction ends up showing that, ooh, you can keep on going, right? X to the fourth, it just keeps on with this pattern. Keep on going. All right, but I'm not going to include it in here. We'll make a note, just a quick note for those of you that pay super close attention. This one's domain, you know, t can be any real number, but yet on this one, your x needs to be greater than 0. And so for all of our examples, for all of these, we're just going to stick with the case of when x is greater than 0 for all of these. And just, yeah, that's what we're going to do. Okay, let's look at an example and see how we handle it. All right, so the first one, in the directions, it says solve the following, find the general homogeneous solution, and that's the reason why it says for x is greater than 0. Okay, so we got x squared y double prime plus 3xy prime minus 3y equals 0. Now, before you can do this approach, you do need to confirm that it's Cauchy-Euler. Right? And it is a Cauchy-Euler equation because you have an x squared as the coefficient on y double prime. The degree on x matches the order of the derivative. Here you've got a 3x, that's to the power of 1, y single prime, those guys match, and then you don't have an x on the y. It's just a constant. All right, so it is Cauchy-Euler. You can't do this if it's not Cauchy-Euler. You can't do this method. All right, now remember, I'm going to do these substitutions. I'm going to say I'm going to let x equal e to the t, right? Which also means, in case where you'll see where this comes in, but t would equal the natural log of x. If I end up getting a t in my somewhere in my answer, then that's where that will come in. I'm going to replace lowercase y with a capital Y, because this is a function on x and this is a function on t. I'm going to replace xy prime with dy, and I'm going to replace x squared y double prime with the d times d minus 1 operating on capital Y. Those are going to be all my substitutions. All right, so in this guy, x squared y double prime, replacing it with this guy. You have a plus 3 x times y prime, x times y prime. I'm going to replace it with a capital dy. And then I have a minus 3 times little y. I'm going to make it a 3 times capital Y equals 0. All right, so then this becomes d squared minus d, but then a plus d. Well, I guess I'll write it out. This is d squared minus d plus 3d minus 3 operating on y. So I factored out all the d's. And then this gives you a d squared plus 2d minus 3 operating on y. And then that factors as a positive 3 and a negative 1. Yeah. You remember our auxiliary equation would be solving for when this guy is 0. So this one would give me a negative 3 as my root. This one would give me a positive 1 as my root. Both of them multiplicity of 1. Yeah. And so Hopefully you remember from, I think it was section 2, how to handle that. That's just the real roots, right? And so your homogeneous solution, keep in mind though, these were all in t's. We were solving for capital Y. Capital Y, which by the way is a function of t, would be C1 e to the negative 3t plus C2 e to the 1t. Coming from, hopefully that makes sense. This is what you're plugging into that coefficient on 3. All right, so that's capital Y, but we want to solve for lowercase y, which is in terms of x. So we need to replace in terms of x so that we can replace it with a lowercase y. Okay, so what I knew was I did a replacement of x equals e to the t, right? Okay, but I've got an e to the t here. That's a straight up replacement. I can replace that back with x. But what about e to the negative 3t? Well, hopefully you remember laws of exponents, that if I take that to the negative third power, I can do that as long as I do both sides to the negative third power. That would give me an x to the negative third would equal e to the negative 3t. Yeah? So that's what I'm going to replace. So that means that little y, now this is a function on x, is equal to c1. E to the negative 3t is x to the negative third plus c2 e to the t was just x. And there you go. Easy peasy lemon squeezy, right? Hopefully. Hopefully you think so. All right, let's look at another example. How about x squared y double prime minus 3xy prime plus 4y equals 0. So I notice I've got an x squared and a second derivative. I've got x to the power of 1 on the first derivative, and I don't have an x on the y, so this is Cauchy-Euler. Yay. So I'm going to do my substitutions of, I'm going to let x equal e to the t. T will be, now I didn't point that out, that we didn't end up having, in our solutions up here, we didn't end up having just a t, right? Times t or whatever. I do an example where we will, but anyway, just I'll write it again just in case if this one pops up with, I've got a t in my solution. Okay, so I'm doing that substitution. I've got little y, I'm going to replace with capital Y. X, y prime, I'm going to replace with dy, and x squared y double prime, I will replace with d times d minus 1, operating on capital Y. All right, so replacing it in this equation, x squared y double prime, I'm replacing it with d times d minus 1 on capital Y, and then we have a minus 3 times xy prime, I'm going to replace with capital dy, and then plus 4 times, instead of little y, I'm going to write a capital Y now, and set that equal to 0. All right, putting together this polynomial operator would be a d squared, that would be a minus d and then another minus 3d, so a minus 4d plus 4 operating on y. Now, does that factor? Two numbers that multiply to 4 and add to negative 4? Yep, d minus 2 and d minus 2. So that means this is d minus 2 quantity squared on y. All right, so that means our auxiliary equation would be solving r minus 2 quantity squared equals 0. So that means your root is 2, but with a multiplicity of 2 because of that exponent on that parenthesis there. And hopefully you remember how we did that yesterday. And that means that capital Y, which by the way is a function on t, capital Y will be C1 e to the 2t plus C2 times t e to the 2t. that was with the multiplicities from yesterday's lesson. All right, so there's our solution for capital Y, which was a function of t. So now, since x is equal to e to the t, then I need e to the 2t. All right, well, you get that by just squaring both sides. That means x squared is equal to e to the 2t. So that'll be my replacement for those. And then remember, here's where that t comes in. Yeah, when you have a t in your solution for capital Y, you're going to replace it with natural log of x. So that means little y's solution, this general homogeneous solution, is C1 replacing e to the 2t with x squared plus C2, again, t will be natural log of x and e to the 2t will be x squared. I had to put the x squared in front of the natural log because that's just proper. You don't put natural log of x and then x squared. If you do, you got to add parentheses and end the parenthesis on the x, so that way it's clear that you're not taking the natural log of x cubed. So it just looks better this way. It's like wearing your shirt inside out. It doesn't look proper if you put that x squared on the other side. So, all right, there you go. There's your general homogeneous solution to that guy. Still easy peasy lemon squeezy, right? Well, as long as you remember all the rules from before, right? Okay, how about another one? X squared y double prime minus 5x y prime plus 13y equals 0. All right, is it Cauchy-Euler squared 2, 1, yep, yep. Cauchy-Euler, yay. All right, so you're going to do your replacements. You're going to let x equal e to the t. I'm going to let little y, I'm going to change it to big Y. This is little y of x. This is big Y as a function on t. We've got xy prime. I'm going to rewrite that as dy. And x squared y double prime. I'm going to rewrite that as d times d minus 1 on y. And of course, remember that t will equal natural log of x in case we get a t in there. Okay, doing our replacements here, substituting x squared y double prime with d times d minus y operating on big Y, and then minus of 5 times xy prime, I'm replacing that with dy, and then a plus 13 times capital Y equals 0. All right, this means I've got d squared minus d and minus another 5d, so minus 6d, and then plus 13 operating on y is equal to 0. All right, so I'm solving this auxiliary equation now. Two numbers that multiply to 13 and add to negative 6, not going to happen. All right, so that means I need to solve this guy. So r squared minus 6r, leave a little space, subtract the 13. Cutting negative 6 in half will give me negative 3. When I square that, that would give me 9. So adding 9 to both sides. This is r minus 3. Quantity squared is equal to negative 4. And then taking the square root of both sides would give me plus or minus 2i, and then adding 3. There you go. There's your roots, right? And do you remember, this is when these are complex roots. Multiplicity is just 1. Yeah. The multiplicity back on this guy, d squared minus 6d plus 13. There wasn't an exponent on the parentheses, so the multiplicity is 1. Your a is 3. Your b is 2. Yeah. And so we've got big Y is C1 e to the at, so 3t, cosine of bt, so 2 times t, and then plus C2 e to the at times sine of bt. Yeah. All right. and we do our substitutions. I've got x was equal to e to the t, so that means to get e to the 3t, you'd have to cube both sides. So e to the 3t will be x cubed. And so now you've got little y now as a function of x. It'll be c1 x cubed cosine of 2 times, oof, all right, I got a t there. Remember, if x is equal to e to the t, t is equal to the natural log of x. Yeah, and then plus c2 x cubed times sine of 2 times natural log of x. Yeah. Could you leave it this way? Yeah, I guess, but we can clean it up using the laws of logarithms. Yeah. And write y is equal to c1 x cubed times cosine of what? Remember, you can take that 2 and put it as an exponent on x. So the natural log of x squared plus c2 x cubed times sine of, do the same thing on this guy. The 2 can come around and be put as an exponent on the x and make it the natural log of x squared. So, either one is fine. I would write it that way. Just because, it just looks better. I think so anyway. Okay, that's it for the examples. I just want to give you one more note. There are times that maybe you can't, maybe it's not Cauchy-Euler, but you could make it Cauchy-Euler. So let's say that. Sometimes you can make it Cauchy-Euler. And it's when you have something like x squared y triple prime, so the third derivative, minus 3x y double prime plus 8y prime. Yeah, I can make this Cauchy-Euler. And the reason why I can is that there is no y term. There's no plus 3y or whatever, right? So if there's no y term, you can absolutely make this a Cauchy-Euler because you can multiply both sides of the equation by x. If there was a y term, you can't do it because then if you do multiply both sides of the equation by x, it's no longer Cauchy-Euler, or it wouldn't make it Cauchy-Euler. This isn't Cauchy-Euler, and multiplying by x wouldn't make it that way either. But in this case, since there's no y term, you can multiply both sides of the equation by x, and that would give you x cubed y triple prime minus 3x squared y double prime plus 8x y prime equals 0 times x is 0. Booyah. There you go. Got Cauchy-Euler now. So as long as there's no y term, if it wasn't given to you as Cauchy-Euler, we can make it that way. Isn't that nice? Lovely. All right. Hopefully you found this one to not be too challenging. I think it's fun. Yeah. All right. You guys have a fantabulous day. Ta-ta.